Hello again. In our last lecture, we talked about how we can use the modes of vibration to uncouple the equations of motion for a multi-degree of freedom system. And that lets us solve for the free response and forced response as well if we wanted. And we kind of glossed over the fact that the damping matrix wasn't guaranteed to actually be diagonal. And so I want to talk a little bit more about that. Before we do, where does damping come from? Say you have an airplane or a rocket or any structure that you might think of. Where does that come from? There are several different sources, and I'll just mention them quickly so you can have some context for what we're going to talk about. So imagine we just had a piece of metal. This shows the microstructure showing the grain boundaries. If we were to apply some kind of load to that, say we put a moment on or bending on it, at all of these grain boundaries we'll get little amounts of slip. As the material deforms, we can get slip in there, and that slip there can cause energy loss, and energy loss leads to damping. So in metals, that's a common form of damping. And we call that viscoelasticity. It's the fact that the material, when it's deformed, it isn't purely elastic, but there's some loss associated with any deformation that we have happen. This is a lot worse in polymers because they have these cross-linked chains, very long molecules. And so you can kind of imagine that if you put a deformation on a polymer, you can get a lot of these chains slipping past each other. And that can lead to a lot more energy dissipation. So typically you'll get a lot more damping out of a polymer than a metal. But anyway, all of that is the first type of damping that comes from the viscoelasticity of the material itself. And that's something that you can take a class on at UW-Madison, EMA 630, and goes into a whole class just on damping right there. Another source of damping is fluid structure interaction, and this is especially important in airplane wings. And the fluid flow around a wing, as you can see in this picture, causes drag, but also if the wing is vibrating up and down, there can be extra energy loss that we can model as damping. And in the field of aeroelasticity, they study this in detail. And an important thing to notice here is that damping can be positive or negative. So we can get damping, or we can actually get energy pumped into the system that can cause the vibration amplitude to increase with time and eventually even cause the wings to break. So that can be dangerous, and that's something that's important to think about if you have things like an airplane or a light structure in the air, or underwater structures. Another sister to that is acoustic damping. These two are basically the same, only maybe the equations that might be used to model them are different. But in this case, rather than kind of flow and vortices and things like that, what we think about is that as a beam is vibrating, we imagine that waves are being carried away. And as those waves are carried away, they carry away with them energy. So that can lead to damping. Usually not important in the air, but in water, that can be very important. Another very common source of damping in structures, and one that's not nearly as well understood as those three I've talked about so far, is friction in joints. So any real structure has pieces bolted together, and you think of a bolt as holding two things together perfectly, but in fact, if we applied a bolt to rubber erasers, we'd expect that they would deform like this. And metals do as well, they just have smaller deformations. And anyway, that leads to regions where you have high pressure and low pressure. So again, if we apply some kind of force or moment to this bolted structure, we can expect that some of the area around the bolt will stay in contact, where we'll get slipping in other areas. And that slipping causes energy dissipation and damping. Alright, one last that I'll mention is nonlinearities. In this class we won't learn enough about that to do much with it, but something to be aware of, that those can carry energy away from the system, and anything that carries energy out of the system can introduce damping. Okay, so now that you have some background for it, how do we account for damping? We went through this very important derivation last time where we showed that we could take the equation of motion and that we could make a substitution. We replace the normal coordinates, the x's, which x's are the displacements of the masses. So if we were talking about this system down here, the x's are the displacements of the masses. And we're defining a new set of coordinates based on the modes. For example, we talked last time about the fact that the first bending mode for this structure is 1, 1. So this new coordinate would have both of those moving together. It's almost like we've kind of tied these two together, and we have this new coordinate, eta 1, that says whenever eta 1 moves, both masses are going to move in sync. Okay, so anyway, we do this change of coordinates, and we have these two important properties, orthogonality properties, of the modes. And so when we plug this into the equation of motion and we pre-multiply by phi transpose, we get this, and we talked last time about the fact that this, these two are automatically diagonal, and if we assume that the damping matrix is diagonalized by the modes as well, then we get uncoupled equations. And so we can solve for the jth mode without having to worry about what any of the other modes do. Alright, so the question for today is, when is this a good assumption? Or how can we realize that in practice? And there are a few different cases under which this can occur. The first one is called proportional damping. And in this case, we use the properties up above to show that if our damping matrix is a linear combination of the mass and stiffness matrices, where alpha and beta are constants, then you can basically just plug in here and show that the first term is just going to give us alpha times an identity matrix, and the second term will just give us beta times a diagonal matrix of natural frequency squared. So if we plug that definition in, we can easily show that the damping matrix is diagonal, and that each value on the off diagonal is just equal to alpha plus beta times the natural frequency squared. So if we knew alpha and beta, we could easily solve this to figure out what zeta is. Typically we don't know alpha and beta, but we might know what damping we want the structure to have, and so we choose alpha and beta to get that. But in any event, this is one way to satisfy this requirement that phi transpose C phi is diagonal. And in this case, we can guarantee that these uncoupled equations are in fact exact, and when we solve them, we'll get the exact response of the structure. So this is commonly used. You'll especially see this in finite element packages when you need to put damping into a finite element model. The downside is that there's really no physical basis for this. There's no reason that the damping should always be mass proportional or stiffness proportional. There are some special cases, actually material damping that we talk about later might often be stiffness proportional. But it doesn't have a strong physical basis, and so that's one downside there. And from first principles, we usually can't figure out alpha and beta. So we're usually having to fit those to some data or something. So another thing we can do if we compute phi transpose C phi and it happens to not be diagonal is to actually just ignore all the off-diagonal terms. Sounds like cheating, right? But we just ignore them. So we do this product, phi transpose C phi, and I'm calling the matrix that we get out C hat. And basically, if we just ignore all of the off-diagonals or hope that they're small, then we can do everything exactly as we had up above. So we have a bunch of values on the diagonal. For each value on the diagonal, we can solve for the damping ratio. And we have our modal damping that we would then plug into this equation up here, and then we would solve it. So that's called the light damping approximation. And Ginsburg talks about the fact that if the damping is light, if the damping ratios are not too large, so for example, if we have zeta less than, say, 0.1 or something like that, that this tends to be a really good approximation. There are special cases where that isn't true. So I'll say this is usually good for zeta less than 0.01 or 0.1. There are special cases where this might be a problem and might lead to some inaccuracy. But usually for most structures that we care about, this is a good approximation. Okay, but this assumes that we have a damping matrix C. And in many cases, C is totally unknown. For example, how would we know the C matrix for this material here, right? It would take a lot of computation and simulating grain boundaries and all kinds of things possibly to come up with that. Maybe that's not a good example because there is an approach to get a C-like matrix for that. But what about the airfoil in the wind, right? Deriving a damping matrix requires simulating all of the fluid flow. So we'd have to have a mesh for all of the fluid and a lot of computation power. And so if our model was only for the wing, we would have no idea what the C matrix is. Similarly with the bolted joints and all of these. So anyway, if we don't have C, and this is actually very often the case, then we just use what's called the modal damping approach. And basically, in this approach, we just take the equations that we get with mass and stiffness. So up above, this would be the equation that we get if we didn't know anything about damping. And then someone gives us the damping ratios, and we go and we just insert those in. We add the damping term here. We just add this term to the equations with the given zetas. So how do people get those damping ratios to give them to us? They might get it from past experience. They might go do a test, as you're going to learn about in this class, and measure them. That's one of the best approaches. Or they might not really care too much about damping and say, well, if we use damping of 0.1%, that's guaranteed to be less than the damping we'll actually have in our structure based on past experience again or something. Therefore, we'll just run all of our simulations with that, and if everything's okay, then we'll go forward and build this. We'll probably build it heavier and stiffer than it needs to be because of that worst case assumption, but we're willing to accept that. Alright, so some examples of modal damping you can find in textbooks and old research papers where people have done tests on steel and found that the material damping from steel is somewhere in this order, 100th to maybe 500ths of a percent typically. They actually tested steel in vacuum, so there was no acoustic damping, and tried to minimize any other source, and that's how they got these kinds of numbers. Similarly, people have done the same kind of thing on composite materials. There the damping is a lot higher, and that's because composite materials are polymers, and so they have more internal friction, more viscosity. Another example of the worst case approach, the FAA mandates a damping ratio based on their past experience. They say if you don't know what the damping of your plane is in the early design stages, you can use 3% and do all of your simulations, and then when you actually get the thing built on the ground and do a test, then you can come in and replace that with the actual damping value if it happens to be larger. So, okay, those are some examples there. This again is one of the most common approaches, I think, and it's an approach we'll use a lot in this class. The last one that I'll just mention quickly is material damping. And again, the viscosity of materials has been studied pretty extensively. And so one way that they put that into the equations is they define a complex K-matrix, where they say that it's the elastic K-matrix times 1 plus I times gamma, where I is our usual complex number. And doing this, you get a complex part of K, which kind of becomes the damping. This only works in the frequency domain, so we can't really go through this. We haven't reviewed that yet. But in the frequency domain, you do get a damping matrix, a damping-like matrix. And so in any event, the book talks through this. For the purposes of this class, if we're given a loss factor gamma, the only thing you really need to know is how do we calculate the zetas. And it turns out that that zeta is just equal to gamma over 2 for every mode. So if you're given a material damping, you can just assume the damping ratios, and so that basically becomes the same as approach 3. All right. So let's look at an example of this. Notice that all of these cases, in every single case, we've assumed that we're going to have some way of diagonalizing the damping matrix. And if we use classical modal analysis, we have to make that assumption, or there's nothing we can do. If this isn't the case, actually, the only thing we've learned so far in this class is to use OD45 in MATLAB and solve it. So we can do that, but we don't have any analytical solutions. In chapter 10 of Ginsberg, he actually shows that you can get an analytical solution for a non-proportionally damped system for any C matrix. And it's not a big deal at all, but we're not going to cover it just to avoid confusion. So I point that out so you know that it can be done, but we won't use that much in this class. All right, so we'll jump to MATLAB here, and I'll show you an example of this. We'll again use our favorite 2 degree of freedom system with the mass and stiffness both set to 1, and we'll simulate the free response to a certain initial condition using proportional and non-proportional damping. So our initial condition has x1 equal to 1 unit and x2 dot equal to 3, say, meters per second. If this was meters, that'd be meters per second. And the other initial conditions are 0. So we've got some instant in time where this mass is displaced over, and this one is moving with some positive velocity. And then we let the system go, and we're wanting to solve for what happens next. So let's jump over to MATLAB, and we will see that and how this can be done. All right, so here's the code. We define the equation of motion, and that if we didn't know anything about damping, we would solve the eigenvalue problem as we talked about last time. And if we did that, let's just run this fresh. Well, no, okay. If we did that, we would get the mode shapes. Here's the 1 minus, here's the 1 1, and here's the minus 1 1 mode. And we get the eigenvalues, and from those we can take the square root and get the two natural frequencies, 1 and 1.73, or close to square root of 3. Okay, so in the case of proportional damping, here's an example. Say the damping matrix is just 0.01 times the mass matrix. We would then calculate this product, phi transpose C phi. And so this is our C hat matrix. And notice that it's already diagonal because we've made the system proportionally damped. This comes out, or sorry, this is C. This is the C transpose phi C. In this case, it turns out to be identical, and they're both diagonal. So to get the damping ratios, we just take each value on the diagonal divided by 2 times the respective natural frequency, and we get that the system has these two damping ratios. Notice we made this mass proportional. The damping is getting smaller as we go to higher frequencies. And you can see that in the equations. If we were to do this the other way, I cleared everything out. Okay, let's just run it again. We'll talk about those in a minute. If we were to do it the other way around, where we make this stiffness proportional, in this case, C is not diagonal. Phi transpose C phi, though, is again. And in this case, the damping goes up as you go up in frequency. So that's one important property of the stiffness and mass proportional damping. They have different effects as you go up in frequency. Okay, so for now we'll just look at that case. Basically, the rest of this I won't go through in detail. I won't talk about in detail. None of this part, well, let's see, this is the eigenvalue, lambda. None of this part will make sense unless you've read chapter 10 in the book, but I put it there just to show that just knowing M, K, and C, you can actually compute the eigenvalues without having to use OD45 or anything like that. And so we get these eigenvalues, and notice the ordering comes out differently, but they are the exact same as the ones that we calculated using the formula above for the case where the system is proportionally damped, where this phi transpose C phi came out diagonal. So the classical damping, or the damping we get using the approximation in this class, is the same as the state space. There's two eigenvalues, one for the positive I and one for minus I. Okay, so now we could compute the response, and we talked last time about this, how we, given our initial conditions on the x's, or here they're called q's, we can compute the initial conditions on eta. We can use the formulas to get the free response of each mode. And then we plot the response versus time. And then to get the exact case where we don't make any approximation about damping, we run OD45 on a system governed by the mass, stiffness, and damping matrices given above. So we use those exact matrices, and then we'll overlay that, and we'll see what we get. Alright, so in this first case, let's first look mode by mode. So eta 1 and eta 2, these are the two modes of the system. Eta 1 has lower frequency, eta 2 has higher. And if we zoom in, we can kind of get a better idea, but yeah, so higher frequency and lower. And then there are some small dotted lines showing the OD45 solution. And if we zoom way in, you can see that those overlay pretty much perfectly. And they should, because the proportional damping is exact in this case. We could do the same thing with the x1 and x2. These are the displacements of the actual masses. And remember, these are always more complicated, right? Given whatever initial condition, the masses are moving back and forth in these chaotic ways, up and down, against and with each other. So the modes match perfectly, so we know that the motion of the masses will also match near perfectly to the precision of the numerical solution. Okay, so what happens if we change this and we make the system non-proportionally damped? Here I'm using this C matrix, which, if we go back to our picture, that's basically like attaching a dashpot. Attaching a dashpot between mass 2 and ground. Or I guess I could have put it over here, actually. So anyway, that's the case that we're solving here. And we'll calculate the damping ratios and we'll see what the response looks like. Okay. So actually, first of all, let's run this case. Run a case that has, first we'll run a case that has a similar level of damping as what we just saw. So we can, again, we calculate C. Now if we calculate phi transpose C phi, we get something that's not diagonal, and actually the off diagonals are just as large as the diagonal values. So we have a pretty strongly coupled system in terms of damping. So you wonder how good it would be to use the light damping approximation on this system. If we calculate the damping ratios, though, and we just ignore the off diagonals, we get these two values. And notice the ordering is different again, but to a few significant figures, we get the exact same damping ratios of the state space system. So if we calculate the response of the system, notice you really can barely even see any differences, right? There's a little bit of difference now between the two responses, but the light damping approximation has just worked really, really well, right? So we are rewarded for being lazy, right? Laziness paid off. We didn't even have to read chapter 10 in the book, and we got an answer that's really, really good. And that's why this is used so much. It's simpler, classical damping is simpler, and it tends to be really good for lightly damped systems like this. We could look at the same in the modal domain. There, we might get a little more insight. But again, you really have to zoom in, and you can't really see much difference at all between the dotted lines and the solid lines. So this has worked really well in either case. All right, so the place this will fall apart, you can't always use this approach, is if the damping gets really large. So if we bump up the damping a lot, so this would be a really heavily damped system, something made of rubber, or something in the human body where there are just hardly any vibrations before everything damps out. And now you see there are pretty big errors that we get by using the classical diagonal modal damping assumption. We can also see that in the damping ratios. So here we're on the order of 10% damping. And if we calculate those using the true formulas, the true damping should have been a little bit different. It's not that dramatic still, but it is different. In this case, if we look in the modal coordinates, these modal coordinates, which we assume are completely uncoupled, that the damping doesn't couple them together, they are actually influencing each other. And so, let's make this wider so you can see. These modes are influencing each other. Oh, I hate when that happens. Let's pop it back out, because I really don't like that editor. Okay, so anyway, there is some coupling here, and the coupling in the damping is captured by the state space approach, or by OD45, and it's neglected by the classical approach. All right, so there's the example for you. We've covered damping, and so now you know what you need to know. And usually we'll use this modal damping approach, and so we're always going to make the assumption this semester that the modes are uncoupled. We might talk a little bit about the fact, about what to do if we see evidence that they're not. Specifically when we do tests and we actually measure the damping, we can sometimes see evidence that the modes are uncoupled. And that comes in as the mode vectors becoming complex. And so when we measure mode shapes, we can't tell the structure we've assumed light damping. It just does what it's going to do. And when we try to make sense of the measurements, we might see some evidence of non-proportional damping. And so we'll watch for that. But for the most part, we will make this assumption, and we'll find that this works really well. Thanks for tuning in, and we'll see you next time.